go. All right, welcome to ECS, CDM 12, Media Computation. This is your fourth class meeting at this point. Third, thank you. Class meeting at this point, and we're going to talk a little bit about push and pop. So we know that P5.js is a state machine, meaning it keeps information around, just like when you press, in Photoshop, you press the rectangle tool stays on until you select another tool. Just like when you put a stroke or a fill color, those colors are persistent until you change them. Now, because we have the power of computation, the power of code, we can do some more sophisticated things. Now, with pushing and popping, what we have is our ability to initially push right away. We can, that blank default slate, we can push it and save it. Just like the metaphor, this is actually a stack. So like the plates you get at the dining hall, you know, they're all pushed down into a stack and you pick the one off the top and another one comes up ready to go. Well, pushing is like that. You are taking the sort of plate as it is now, like the default state when you start. If you do an initial push, you push that into the stack and you have a new plate to work with. Push it down. And then you can make all the changes you want on the plate that's on the top. And then when you pop it, you take that plate off the top and discard it. That leaves that original blank slate underneath for you to work with. So what push does is it saves whatever current state you're in. You can write on this new state and then pop to get rid of all those changes you did and go back to something else. This is what I want you to do with this exercise. That's why we have this push and pop here. Now it's pretty handy. Let's see if we can just make a little bit of code here. Let's make a new sketch. Fine. Get out of here. Side by side. By default, it draws circles. We don't need it to draw circles though. We want to go ahead and push. Now let's translate. So what does translate do again? Yes.
Does it move the point of origin to where you want it to be?
It moves the point of origin to wherever you specify it. Well done. And that also is meaningful for rotate, because you probably dealt with pivot points in 3D or 2D modeling software, 2D drawing software. The pivot point is where, when you rotate your paper, your surface, where do you rotate it around? What point do you rotate it around? And so by default, rotate works at 0, 0. So like the example in class, if we wanted to have a rectangle, rect, and let's put it 100, 100, make it 100, 100 big. Right, if we do this, and see what we have. Nothing. We have a rectangle here. Let's go ahead and set the background. Okay, and we'll do this. We'll make a 400 by 400 canvas, so we know exactly what we're working with here. Whoops. And we'll make that canvas black, so we can distinguish it from that background color. Great. I'm also going to put just a small box at 0, 0, so we know what's there. Rect 0, 0, 2, 2. Oops, my bad. I've been using OS X keystrokes all day. Oh, and I'm not logged in either. Okay, fine. One moment. I had this all ready to go. Okay. We'll fill it with white. Put in our semicolons. Make it big enough to see it. Great, okay, so there's our 0, 0 point. So now when we rotate this rectangle, we're rotating around the pivot point. So if we rotate 45 degrees, here we won't make a diamond. What we're going to do is rotate that sucker almost right off the screen. So we're rotating 45 degrees around this point, which pushes it from here all the way to here. And so what's kind of fun is we have this thing called frame rate, our current frame. And we can use a little bit of math. So we can take the remainder of that current frame and 360. And so what we're going to get is like this rotating. I'm sorry, I must have gotten the wrong frame count. I'm getting two environments mixed up here today. There we are. Right, so we're getting we're rotating that square over and over and over again. But we're also doing we're having a problem that we've run into a lot, which is we are rotating in radians and not degrees. So angle, mode, degree. All things we've talked about last class. I'm going a little fast here just to show off a particular point and not to focus on a lot of the details. Degrees. Right, so we're rotating around this particular pivot point, and we're drawing 60 times a second. Right, so we're just overlapping 1 degree at a time. Now, if we wanted to rotate that square, we'd want to set the, we'd want to translate our pivot point to be in the middle of the square. So the middle of the square in this case, since its top left is at 100, 100, but it's 100 wide, 100 tall, the middle would be 150, 150. But that didn't quite work. Can anyone tell me why? Yeah.
Because we translated before you drew the rectangle, so the rectangle drew 100 away from 150, 150.
Exactly. Our origin now is in the middle here, but I didn't change the left and right coordinates of the rectangle. So now I'm actually drawing 100 and 100 away from that changed, altered origin point. Although it's kind of a fun circle. So now, since we've already changed the origin, 0, 0 to be where we want it to be, we can draw our rectangle at 0, 0. And now we have a rectangle that spins around. I said it right and then did it wrong. 100, 100. Translated 150, 150. So I'm rotating around that top left point. Oh, that's right. So now I have 100 by 100, and if I want the center to be at the middle, now I have to draw the rectangle offset a little bit, offset by half the height and width, so that that origin point's right in the middle. There we go. And so now we're drawing a spinning rectangle. Now, that's neat. But we can say this later. So I'll give you this sketch. I'm going to do a multi-line comment just to get rid of what we have. And let's perhaps make a little clock here. Let's do a rect. We'll have the top be at 200, 0, and we'll make it 10 wide, 25 tall. Right, so I've got one little tick. Now let's say we want to rotate this tick around the clock. We can do the same thing that we did before here. You know what? I think I may give this to you as an additional sketch with an annotation. I think this may take a little too long for what I want to do today. But the goal here is that we want to show off push and pop independently. So let's say we want to have a clock that says, let's say, 3:30. And so let's make this be the hour hand. And then we want a second hand. Seconds hand? Minutes hand. What am I thinking? Hours and minutes. Take our rectangle here. We're going to make it a little longer. But right now they're both pointing at noon. So it can rotate what I said, 230. So we can make this 180 and make it point at the half hour. We've already set our degrees. Angle mode radians to degrees. And we need to change our pivot point, which we will set right in the middle of our surface, 200, 200. And that means our hour hand, our rect, now needs to be above that. So let's do 0, so it'll be in the middle, we want to be 0, so it'll be in the middle, and negative 200, so it'll be at the top. All right, and now we can take our other hand. We can actually start at that top point as well. And we rotate 180. And now we have our hand at the bottom, right? So we've rotated, we've set our minutes here. We translate to the middle. So the middle origin point is right here. We have our hours hand, which is pointing at the top, pointing at 12. We have our minutes hand, which is pointing down at 6. And now, here comes the thing that's interesting. So now we have our rotate. We want to make our hour hand move over to 3, right? So that is a rotation of 90. But I did it before the translation. Messing up my own example. There we go. But what happened here? Why isn't this right? We rotated the first one by 90 and the second one by 180. Shouldn't that point to 330? What happened here? Yeah.
The rotation of 90 degrees also affected the second rotation because you didn't do the push pull.
Exactly, right? So we have the first rotation being additive with the second. So the second one rotates it by 180 more, which puts it at 270 rotation, which puts it at the 9 area. So this is where push and pop come in well. So we want to keep that common origin point. So we can push here, draw our hour hand, pop it, and then that will sort of remove this 90-degree rotation. We'll push, do our 90-degree rotation, pop it, which would remove the 90-degree rotation, and then we'd be off to the races with our minute hand. Right, so this is the bit of example I wanted to show you. I've had a lot of questions on this, so I wanted just to show you a little bit of this sort of like rotational dependency and how push and pop work. All right, did I confuse you more? Did I answer some questions? Do you have any thoughts on this? Other than me fumbling at the keyboard here, being nervous in front of class. Okay, great. And this will be on the recording, so you can refer to it. We've historically just had a lot of problems with this push and pop and people like actually grokking and understanding what's going on enough to reproduce it. So those of you who have this already, thank you for bearing with me. And for those of you who learned something, thank you for that as well. And let's get on to the lecture content for the day. This web frame drives me nuts. Okay. Now it's loaded. All right, so we're going to talk a little bit about computer organization. So last class, we had talked about shapes and colors, readability of your code, and basic transformations. Right, they gave us a palette to work with. We could do colors, transparency. We talked about color theory and gamuts. We had this basic idea of what commands are and how to parameterize them, how to move them around. I love this example that we just did with the clock hands. Now, we're going to dig under the hood just a little bit more and talk about what's happening, what a computer actually does for us at an abstract level to help us better organize our code and do computational tasks for us. And does anyone recognize the game that this image is from, the GIF is from? Yeah?
Manifold Garden?
Manifold Garden. Do you know anything about Manifold Garden?
I mean, it's like a weird abstract, I don't even know how to describe it, like perspective messing with, like, I don't know.
Yeah, it has a lot of non-Euclidean geometry, meaning that it's not the normal 3D geometry we're used to, but it's also procedural architecture. There are algorithms, which we know are these step-by-step instructions that help us do things. It has algorithms in it to construct, on the fly, through computation, these weird architectural forms. And there's gameplay around that. It's a playable art piece. So let's talk about processors. So these are the motive parts of a computer. These are the things that actually do the math. They execute instructions. For us, they're these little agents that can perform a very limited set of tasks very quickly. They're also called the central processing unit. I'm sure all of you have heard the term processor before. Central processing unit is becoming a little bit antiquated, but these are your Intel processors. These are your AMD processors. These are your Snapdragon chips in your phones. This is the processors behind the Apple Silicon, the RISC processors in your new Macs. A lot of them are multi-core, which means there's multiple processors inside each one of your processors. That means it can follow multiple instructions simultaneously. But you have lots of other processors in most computers. I'm sure many of you have heard about graphical processing units, or GPUs. These are the things your crypto bro friends really like because they mine cryptocurrency. What they're really good at is actually graphics, doing graphics operations. Hence the name graphics processing unit. They're historically the animating force, the market force that made these come about were people playing video games on PCs for personal computers. And these are the things that do the calculations that make 3D physics work, particularly matrix calculations, vector calculations, and doing a lot of these simultaneously, instruction streams simultaneously on various data streams coming through. And they're chunked out into things called stream processors, and there's a lot of them. There are more stream processors on your graphical processing unit than there are cores on your central processing unit. Right, so they do this sort of graphics processing very well. There's also physics processors that specialize in the math and very quickly computing math behind physics. Things like doing distance calculations, 1 over the square root of x to see the effect of, or to calculate like the distance effects for things like gravity. And there are digital signal processing units. For those of you who are into computer audio, there's plenty of these things around. Computers also consist of a large storage space. Huge warehouse, full of boxes, full of little bits of information. So this is what we call memory, random access memory. There's also a little bit of memory on your processors, for those of you who really care, L1, L2, and L3 cache. There's also little set of boxes associated with your graphics card. There's graphics card memory now. There's also your hard drive is another set of boxes. This is where your MP3s and movies are stored. Your homework is stored here. This is persistent storage. what other data warehouses, data storage areas do you think your computer has access to? I bet you're using one for this class. Yeah.
The cloud.
The cloud, right? So we've externalized a lot of this. We've virtualized storage on our computers to be on other computers through network access, right? There's also, your USB drives, Bluetooth devices sometimes have a bit of storage. You can sync data via Bluetooth. It's not a super good idea, but it works. You have your own network storage sometimes on your routers. Some of you have set up a Plex box or something to watch videos. Those are storage as well. So there's a lot of little bits of storage out there. And it looks roughly like this, right? So we have to know where to find a box. That is the address. So in this big chunk of memory, I imagine most of your laptops have 16 gigabytes of memory, 32 gigabytes of RAM? Maybe your phones have a little less. Well, each one of those bytes has to be addressable, meaning you have to know where to find it. And we talked a little bit about this last class, where we went from 32-bit machines to 64-bit machines. That opens up a lot more addresses. So now we have 2 to the 64 addresses to use instead of 2 to the 32, which means we can now address things that are over 4 gigabytes, which is great because every 4K movie I've ever downloaded has been way bigger than 4 gigabytes, right? Individual asset files from Call of Duty are way bigger than 4 gigabytes. So we need this. So our address space, or this sort of like bit range, this tells us how big that address can be. In this case, it's 4 bytes. And so that means we can address values, right? So we have these addresses, these boxes sitting around at different locations in memory, but what's in the boxes? So these memories, these bytes can each be addressed. They have an individual identifier, a where they are physically on your RAM, on your chips, on your machine. Now they actually have content. Those bits can be set to values. So that's what this right-hand side is showing. That if you go to, let's say, your very first bit, in this case, its value is 3. And we're assuming this is a Boolean value, right? Because we addressed by powers of 2. This would be 0, 0, depending how big it is, a bunch of zeros, and then 2 ones at the end, which would be 2 to the power of 1 and 2 to the power of 0. So 2 plus 1 together is 3. So same for 17 and 2. So now we have values stored at locations. We know how to store values. We can go to an address, change its number. We can look at an address and retrieve the number. So that's great. Now we have a bunch of things we can store. Now we have memory. And memory is great for us. This is where we store data. So we can interpret these values as numbers, as texts. As texts, we call those strings. We'll go over strings more today. They can also represent images, sound, etc. All the assets that you have on your machine. Sound files like the opening of the startup noise of a MacBook, right? It's right there inside of a set of bits represented on a disk. Those bits are read, interpreted, and played out as sound. And so programs are this. You compile a program, you run a game, you run the calculator. That's just a set of values stored in your memory somewhere. But we interpret those values in a specific way. We interpret them as a list of instructions and not, let's say, as an image or a set of numbers. Right? So the interesting thing here about computers is it's really how you interpret the data that's there, as well as the data being there and being able to be manipulated and stored in the first place. So, list of instructions. Well, we have a central processing unit that takes instructions. So we have things now stored in our memory that can be used to say, hey, to tell our processor what the heck to do. Right, so we have our processors, we have memory, they look at the data that's stored, the set of instructions that's stored inside of our memory area. We interpret those as programs. And those programs, they need stuff to operate themselves, right? You can run a program and it can do its own particular thing. But for us, as people who care about computational media, we care about what the programs think about, what they consider. And one of the big things we can consider is input, whether it's from a keyboard or a Nintendo 64 controller. Is that an N64? If I'm seeing it from here. It can take an input from the internet, from your webcam. You can take input from all sorts of sources. But what does it do with it? Well, it can either change the memory it can change memory values and do some math computation for you and give you results. Or it can output things to the screen, to the printer, to the haptic device, to your Blue Sky feed. Right? So we have stored programs that can do instructions for us. The processor looks at those programs, does those instructions, takes in input, and provides output. This is the basic model of computer programs and processing. There's a lot of details internal to this, but at sort of like this level of understanding computation in a way that can help us create media, this is a good way to conceptualize it. All right, so I'm curious. Literacy at this scale is all over the place. How many of this is this sort of like review for you? Okay. So we're hitting on some juice here. Do you have questions about this? Things on memory, interpret as instructions by a CPU. CPU changes things in memory, considers things in output, or considers things coming in from input, and gives us output. The output can also be things like instructions to a 3D fabricator or to a laser cutter. And so we have the processor and RAM working together to do things on the fly. But if we want to store those in the long term, if we want to store output like an image or a set of calculating numbers of pi to as large as we can, which is a classic first year computer science thing to do, we want to keep those results around somewhere. And so we put them on persistent storage. The cloud, one of our disks. Does anyone know what this is? Other than just an icon? Yeah.
It's an HDD.
An HDD. What's an HDD?
Hard disk drive.
Hard disk drive, right? It stores information in a hard way, meaning it's persistent. It's also physically very hard. And it's got this rotating disk. And it's got this little reader right here, which is this precise instrument that can read bytes and streams of bytes off of this spinning disk that runs usually at 5,400 or 7,200 revolutions per second. You can get really fast ones that go over 10,000 revolutions per second. I swear those things are going to fly apart. They sound like airplanes. Now we use solid state drives. There's no spinning media, which means it's just all electronic. But this is a common form. Your data is, all of your emails, your images that you have cloud synced, they're all sitting on a hard drive in a computer somewhere on the web. Probably one that's just like this, except they're in hot swappable drive trays. You've probably seen NCIS characters sneaking around data facilities with blinking lights and it's dark. There's a lot of those in there. Yeah?
Is that similar to a floppy disk or?
No, floppy disks are a little different. It's a similar idea. So floppy disks are little magnetic disks in a small plastic case. And the original ones were 5 1/4 by 5 1/4, 5 inches, quarter inches. And they could bend and they were black and bendable, typically black. And you slotted them into a slot in the side of the computer and you closed the drive bay and then your computer could read it. This, on the other hand, is something that you typically, while your computer's off, you plug this in through usually a SATA cable or some hefty data cable that's on your motherboard. And then you put power into it. It has to be powered by your power supply. And then that drives a pretty hefty motor on this thing that spins the disk. Now, fundamentally, they're both just magnetic tape. magnetic objects that can be read from and written to by a little magnetic arm or reader. So they work into the same principles, but floppy disks at most store like 1.4 megabytes, and now these are terabytes. Right. So great question though.
What did you say that was called again?
This is a hard disk drive. And these are pretty easy to find. You can go like on Newegg or whatever. Most of your machines have either one of these in it or a version of it that has no moving parts that's sort of like a USB drive but more robust and permanent. Oops, I went back to this. All right. So we talked about hard drives. Now, hard drives store things for us, right? They store our files, they store our pictures, they store our programs, they store our operating systems like Windows or Mac OS or iOS. Now, inside of those, there's an abstraction here, which is historically not always, this hasn't always been the case, but for modern computers, almost all of them use this metaphor, where there is a hierarchy or a tree of folders. And folders can contain other folders or files. And this is the basic way that files are stored in our computers. You know, you can open your Windows folder and see all of your Windows DLLs inside, or you have your user folder. For mine, it's usually called Josh. Yours is probably called whatever your name is, or whatever your game handle is. And inside those, like, is a folder for your desktop, a folder for your documents, a folder for your downloads, some hidden folders for your application data, things you have to go into menus to say, hey, show me hidden files and folders, so you can see those. So each file and folder has a set of properties, a set of reading permissions, a file size. There's a lot of mechanism that goes around folders and files. And that helps us keep our information safe, keeps us a little error free, and helps us manage the storage space so we don't lose a lot of it on our hard drives or on our hard disks. So, you know, just about everything that you have downloaded is on here. If you have like iTunes and you have like stuff on iMusic, a lot of that is synced to your computer. Then your computer transfers it over your USB cable or wireless to your phone. And so now you have the same music on your iTunes on your computer as you have on your iPhone, that sort of thing. So we have a lot of automatic file management for us that's happening on our behalf to make our lives a little easier. But under the hood, you can do a lot of this management yourself. You can copy files, paste files into other folders. I'm sure most of you have had to deal with things at this level before. But now we know that just about everything is a file, including your programs, but all of these things are also moving to the cloud. I'm sure many of you have used a Chromebook. There's not actually much of your own content on a Chromebook, and all of it is sort of like synced over the network to things like Google servers. Right, and so now I want to reiterate just a bit of our last class. So why does color go from 0 to 255? Well, now we know this because of these bits we have in values. So now we can store bits at a memory address. So now we can say, hey, I want to store this color value, this background color that I want to use again and again and again. We now store that in our memory somewhere in one of those addressable boxes. And so we had this look before. So inside of the boxes, if they were 3-bit size boxes, we could have up to the number 7 stored. We could have any number inside that box from 0 to 7 just by changing the bits inside that box. But the address of the box stays the same. Variables. So this is a core concept that we're going to know for programming, this idea of variables. And what these are is this helps us use our memory and use our boxes in our programs. In the very old days of computer science, I guess the really old days were like you punched holes out of punch cards and those were the 0 and 1 bits that you gave to the computer to work, that was your program. You had to punch it into a card, into a punch card, and then feed it into the machine. But after that, we started storing more things on disk, but programs were direct processor instructions. Add this memory register to this memory register, move it to this memory location, all in binary hexadecimal values. So variables in higher level programming languages have helped us move away from dealing with individual memory values and let us deal with something much more human friendly, particularly names. So high level is a variable is a box in a warehouse that we can store information. By declaring a variable, we are now getting a box that we can use. The variable now represents a box, and we can put whatever information we want inside that box. It's a memory location that holds a value. So 2 parts of this, and you've seen this in some code so far. First, we want to declare the scope of the box, or where in our program, in our code, can we see this name that we're giving a box, and the name of the box itself. We have a box that says background color, where we store the background color that we want to refresh to instead of just giving it a raw color value. Let's say we want to change the background color over time, or as things in our program change, maybe we map the background color to the phase of the moon, or the actual color, the light value outside. So as it gets towards dusk, we start turning a ruddy orange, and then we start moving into a dark midnight as time progresses. Now, instead of making a bunch of background calls, we can simply change a value inside of our background color variable and give that variable to our background function, our BG color function. We can give it red, put it in the box. So we need to declare variables before we use them, and this is what this looks like. We use the term let. So let count has given us a box. The box doesn't have anything in it right now, or as a default value in the box. But right now, we have 2 boxes, count and finished. So what's this actually doing? So first, it's telling us to reserve some space in memory, aka give us a box in the warehouse. And because it's JavaScript, so we have some information, since we know there are different types of things that we can store in a box, a number, a string, etc. It makes sure that we have enough space in the box to store the thing we need to store. In other programming languages, and in the past this was done in languages where you had to really upfront specify how big and what shape you wanted the box to be, JavaScript on the fly dynamically helps us resize and reinterpret our box. So it's kind of neat. So the label, such as count, or whatever other name you choose. Whenever we use that name in our code, that basically points to an address in the warehouse. So we get a shortcut label. We get a nice handy way, a nice address, a nice handy way to specify this. Instead of memorizing the address of my home, I can just put in home, right? And associate that with a more complicated thing. So we don't have to deal with a complicated form of where count is stored in memory. We can just deal with the name count itself. And you can put data into count. Right here, we can put the number 3 into count with this right here, with the equal operator. Now, this is a little different than math. So math, you're looking at both sides and checking to see if they're equal and things seem equal or not. You're bouncing out an equation. Here, you can think of this equal sign as an assignment operator. It is assigning the value of 3 and putting it into the count box. Assigning the value of 3 to the count box. Taking 3, putting it in the box. So the box name always goes on the left-hand side, an equal sign, and then the value you would put in the box goes on the right-hand side. and then we can use it later. Like we can use the number that we stored in that box as the first parameter to say rectangle. I don't, you will not be tested on all this. You'll be tested on maybe through BigInt. But these are the basic primitive types, the types that are inherent to all JavaScript programs. These are the basic types. A string. So we've looked at strings before. We put in white, black, aqua, lavender, cornflower blue. These strings are just a sequence of characters. They're called a string because in computers, each character used to be represented by a byte. And they were their own data structures. And you had to have a whole bunch of them together to make a word. So these are individual characters strung together. That's why they're called strings. It's a string of characters. And then we have number. So this is a decimal value. So we talked about our numbers before, our powers of 2. Those didn't actually have any decimals. You couldn't have a value, a fraction of a value in there. But numbers are stored in a different way. They interpret those bits in a different way so that you have a point that can, or you have a number that can be more whole number like. I'm sorry, more real number like. Then we have a Boolean. So Booleans are great. They're a 0 or 1 value interpreted as true or false. This is going to be really handy for us because we're going to be needing true or false values. Let's say you're making a simulation or a set of bubbles and you want the bubbles to stop, like we saw in the example the other day. You can have a variable that says bubbles going, and it can either be true or false. If it's false, the bubbles aren't going anymore and you want to stop them. If that value is true, you want to continue making the bubbles go. And we'll get into how to handle this sort of like conditional code very soon. But they run on these Booleans, these true or false values. And then we have BigInt. Because numbers can do a lot for us, BigInt is a special thing. BigInt can handle extremely large values. It can handle like values I think higher than I know what the number is, like how to say the number. Like over quadrillions of values. So this can handle your very large whole numbers. And you have to ask for one specially. These don't come out of the box. They are implemented by JavaScript, but you gotta ask for them, and we'll do it eventually. And then we have some more esoteric ones, some ones that really help the mechanisms of the language work. And we have undefined. And that's when you don't have a value. Maybe you know something is a string, but it doesn't have any value in it or something. And then we have null, which means there isn't even an object. The box doesn't actually point anywhere. It's a dead box. And then we have a symbol, which is something that's for unique and immutable keys. Don't worry about it. I'm putting it here for completeness. I want to make sure you at least have the spectrum of things. And then we have an object, and objects are interesting because you can make your own sort of data structures past these primitive types, and we'll talk about that just a little bit in class, not a whole lot. But there's a way to store, anything in a box, and that's what objects do for us. So variable names, they are single words, meaning they don't have any white spaces, like we talked about before with camel case. That's a way of making sure we don't have any white spaces in our names. So just like our command names have no spaces in them, our variable names follow a very similar set of rules. So it can include an underscore, a $, characters, and numbers as long as they aren't the very first thing in the name. And you can't use the reserved words for the language, so ones that are already used, like let or function. Or var. So let's take a look at some of these. Let count. Do you think that is a variable name given our rules? The ISR sweeps through the plains. Is count a variable name? Is it valid? Yes. It is! Thank you! Oh, come on. Okay. The check mark worked. Okay. What about let? Is let a variable name? No, because that's a keyword. What about one choice? Maybe I should have changed it to piece. No, it's not. What about choice 1? Yes, it is. All right. What about back count? No, it's 2 words. What about back count? Yes. What about back count? Yes. What about back count? No, that's a dash. That's a reserved keyword. That's minus. That's subtraction. No. So these are the basic rules you're going to want to use for your variables. And, we'll have some more examples of this. This is just a rough and ready little gut check for you if you want to go back and look at the slides. So variable assignment. You assign values of the equal sign. So we make a variable a. And we assign a value of 3 to it. You could also assign it to be the value that's a result from an expression, such as an arithmetic expression. 4 times 7 divided by 2, which is I'm making you do simple arithmetic. No! 14. Thank you. Yes, 14. And you can use variables in expressions, and you can use variables to pull and extract the value from the box. So let's make the value. Let's continue our statement and add a let b after on our 4th line here. So first line is let a, second a equals 3, fourth a equals 14 after evaluating the expressions. 4th line is b. And so now we have b equals a plus 45. At this point, what is b? What has been assigned to b? 14 plus 45. 59. Thank you. So b is 59. So now we can draw a rectangle with these numbers. So now it's 100, 100, 59, 14. So it's 59 wide and 14 tall. Right, and this is great. So now we can start using these variables to control things, to save values for us. That helps us deal with information change over time, which is what we're building up to. All right. And you can create your own variable types, and we'll get into this. We'll do some structured types. We won't make a lot of very big data types in this class, but we're going to show you how to use pre-existing non-primitive data types like color. So color holds an RBG value, like we said. You can use a color data structure inside of fill. So we'll take a look at that in a moment. But we can also get values. So this is a cool function. This get 1015. If you look up this up in the documentation, it actually looks at your sketch and finds the color value of the pixel at 1015 and returns it. So let's say you pull an image off the internet and you put that on your canvas. Now you can see what each individual pixel value of that image is. So we got a lot of power here. We can actually directly play, read, and write to the canvas. You can get and put to put values on the canvas directly instead of using a circle or a square. You can individually manipulate pixels. Here's a little more complex of an example. We're going to let C1 equal color 204, 153, 0. And then we're going to let color 2 be a hexadecimal color, like an internet-based color of pound FFCC00 or hash FFCC00. We're going to turn off the stroke. We're going to set fill color to C1 and draw a rectangle at 0, 0, 25, 100. So we're going to draw color 1 right here on the left. Then we're going to set fill 2 to color 2 and draw the middle rectangle. Then we're going to set color 3 and we're going to get 1050. So get 1050. Set that C3, fill C3, and draw a rect here, right? So we're actually referencing a color that we put it on the canvas to put a new color onto the canvas. Any questions about this? I can tell some of you I'm going too fast and some of you I'm going too slow. Trying to make a happy medium here. If you have questions, please speak up. And you can see the reference for the color library here. There's a lot of really interesting information in colors. So this is where I have to disambiguate. You're going to see a lot of examples in the internet, a lot of examples that are on openprocessing.org, a lot of examples that are on p5js.org, where they use the var keyword with variables instead of let. So let is a little newer in JavaScript land. Var used to be the way you declared all variables. The difference is in where you can see those variables in your code, because you can't see them everywhere all the time, unless you use a global, which we'll talk about in a moment. Now let makes the variable visible in anywhere inside the curly braces that you define it in. So if you define at the top of draw, you can use it anywhere inside of draw. If you define it at the top of the file before setup, you can use it anywhere in your file. Although I should say there's an implicit set of curly braces around your file, so it can't be read in other files. This is in contrast to var. var is just slightly different. That makes your variable visible, your box name usable, in the function that you define it in, which is a little different. That means if you have a function and then you have some sort of construct in the function that makes other curly braces, and you define that var inside that secondary set of curly braces, it's visible in the outer set as well. You just go down to where is the function made before your var. And we haven't talked about functions yet, so this is a little confusing. But we'll reiterate this when it's more meaningful. Now, globals. These are visible anywhere. So a lot of the P5 classes that we're using, color, setup, draw, those are actually globally visible commands. You can see them anywhere in any bit of code as long as you have, so like this library, your code loaded. Now, if you make your own var, instead of let, you make your own variable with var at the top of outside of any of your curly braces in your code, that makes it global. That means that any other code can read your variable. And that's powerful. That also means that if you use a variable name that's common, you're likely conflicting with someone else's variable name. And you may be fighting for control of it or what values actually go in it. You, using a common variable name, can easily overwrite things that other areas of code that are working on your behalf are doing for you. So this is why we typically don't use var and we use let instead. It keeps things local, it keeps things in our project and not just willy-nilly going around and impacting all sorts of other code. So it's not a good idea unless you sort of like know what you're doing. All right. Any questions on let versus var? You should be using let for this class. Unlike semicolons versus not semicolons, which I'm letting you use as an individual choice, you should be using let for this. And as per my notes, I wanted to just reiterate about semicolons. They used to be mandatory in JavaScript. They are no longer mandatory. You should pick one, either all all semicolons or no semicolons, and use that persistently in your code. We'll dock a small number of points if you mix and match, if you have semicolons in some statements and not in others. Like just pick none or all. Why would you pick one or all? Well, if you're wanting to specialize in JavaScript, or none or all, if you like to specialize in JavaScript, non-semicolons is sort of the way JavaScript development is going. So you want to practice that. But if you want to learn C# to make games in Unity, or C++ to make games in Unreal, those are semicolon-based languages. So you probably want to get in the practice of using semicolons in your code. Make sense? Lovely. All right. We're going to go through some samples ourselves. So variables are useful when things change. They're used for layout. So when your screen size or your canvas changes, someone resizes the browser window. All of a sudden, things may go off the screen, or your HUD that shows your ammo and life may all of a sudden need to change size. So variables are good for helping you be reactive to those changes. They're also good to make something depend on someone else, on something else. Let's say you want to have a sphere that orbits a rectangle. Well, you should know that rectangle's locations so you can figure out where you are in that orbit. As the rectangle moves, your circle should be moving to keep that orbit steady around it. So keeping the location of your inner rectangle, keeping that in a variable, lets your circle reference that variable and keep them all synced up. And used to vary something over time, right? We can have, if we redid our clock example, we could have had a variable for the degrees that manage the hands of the clock instead of just relying on frame count, which frame count is a variable given to you by P5.js. All right, so I want to just take a beat here. We went through quite a bit. Questions, comments, concerns before we look at some code? We'll just have a moment of Zen silence. Okay. Let's take a look. Let's take a look at strings. So I want to do more with strings. Let's learn more about strings. Is this legible to folks in the back? Bigger? We're good. Okay, I get thumbs up. Okay. So this is a sketch. I'm going to go ahead and put it on Discord. Maybe Discord will just update for me. Okay, so we'll go ahead and put this into Media Computation General. There's a sketch I'm using right now. So we're doing setup. What does setup do again? What is this function setup? What does it do? We're reiterating because reiteration is good for learning. How does one use setup? What does it do? Is it magic? I think it is sometimes. Sometimes it behaves erratically. It's the code that's ran right at the beginning of your sketch. And after it's ran, then it'll start doing draw over and over and over and over again, by default 60 times a second. All right, no smooth. Much like my delivery, it takes out the jaggy bits of the text. So this is just to make the text a little more readable on mobile screens. It turns off anti-aliasing, which turns out to be a problem with text in browsers. Does anyone know what aliasing is? Anti-aliasing? Have you turned it on your computer settings? Yeah.
It's like a gradient for the text to make it appear higher resolution on low resolution screens.
Exactly. So you may often see geometry on your screens and it looks a little jaggy. Anti-aliasing looks like spreads out that jagginess over adjacent pixels and makes it look more smooth to the UI. Does a little bit of pixel color averaging. All right, so we're turning that off because it gives us problems sometimes. All right. So now we're at draw. We set our background color to lavender. And we set the fill color to cornflower blue. And we're going to use a new command called text. As you can probably infer, text puts text on the screen at a position. So this gives us a few more commands to work to use with it, to use with text. One of them is text size. So I'm setting the text size to 32. So the first thing I'm doing here is drawing the strings at position 1040. So that's this one right here. And have you all been able to access this? Okay, great, thank you. To making sure I had the permissions correct. And now we're dropping the text size down a bit. We used strings as a header. So now we're going to use slightly smaller text for the rest. So this has some comments in to help you out. One of the cool things about strings is, they're just sequences of characters smushed together. So you can smush together even more things. So here we are putting a string together. We're putting the string CON together with the string CAT, with the string EN, with the string AIT, to make the word concatenate. And that is technically what's happening here. This is what we call appending strings together, concatenation. This is taking strings and just merging them, joining them. And we're drawing that at 12, so it's a little more indented, and down a bit at 75. Now, variables can store strings. And strings can be either in double quotes or single quotes, or backticks, but backticks are special. We'll talk about those separately. And just like semicolons or semicolons are not semicolon, I would pick one of these to use with strings and use it all the time. I personally am used to double quotes, so I use double quotes, but single quotes are just fine as well. So here, my cat is the string Chunky. My variable dog is the string Derpy. And we can use our string variables with concatenation to form new strings, which we're going to put out at 12,100. So cat is plus cat, concatenate Chunky. Cat is Chunky. And dog is, cat is Chunky. Dog is Derpy. Right. So now we can use variables to change text over time. Health, equals health value. Now, what's great about having both of these single quotes or double quotes available is that you can use the opposite one inside of it without doing some extra work. So for instance, if I use single quotes, I can use just double quotes inside of it freely. Meow! Exclaimed cat. And so the backticks are something special. These are called string literals. Basically, what you can do is you can embed variables with this little bit of $ curly bracket syntax inside the string. It will replace this whole bit with whatever variable is in the value cat. Whatever value, string value is associated with the variable cat. So cat is cat. We know our cat value here is Chunky, so this should print out cat is Chunky, which it does right here. Now the print function is different than text. Print puts values out to the console. Where is my console? At tutorial mode, editor, console. There we go. So you see print output strings to console. That's exactly what we put in this. Notice this number is getting bigger and bigger and bigger. So we're doing this once each frame. And so we're printing, so far we've printed close to 1,000 one of these strings out to the console. This console is handy because you make little notes to yourself that don't show up on the screen. It's good for trying to understand what's going on with your code without having impact the experience. Did you know you can use emojis in your strings? You can. Use the rainbow. these string literals keep formatting and they keep line breaks. So you can take this chunk of Eve from Rainer Maria Milke's poem, this fragment here, formatted as it is with the line breaks, and print it out directly. So we got a lot of flexibility with strings. And we can use this directly. A long variable name that's meaningful. I torture my students and the people I develop with long, meaningful variable names. Harmpreet snickering. All right. Now, because these are just sequences of characters, strings of characters strung together, we have ways to access an individual character, an individual letter out of these bits of text. So cat, character at 4. This is computer science. We start counting at 0 because we use index offsets. So cat, the variable cat is chunky. So C is 0, H is 1, O is 2, N is 3, K is 4. So this character at returns a K. We're going to smush it together with dog at character 1. So the second character in dog is derpy, so it's E. And then we have just a string here, elderberry. And we're taking the 9th position character from it, which is the 10th character sequence, which is the Y. And so K plus E plus Y is key. All right, now we have 2 variables. Lower, which is in uppercase, and upper, which is in lowercase. There are commands that you can use with your variables to change their properties. So in this case, lower, the lower variable name, we use here with a dot notation. A dot is basically saying this string, this function, this command operates on this variable. And so there's a set of these, like 2 lowercase and 2 uppercase, that work with this dot notation on variables. And so what this does is it takes this string and makes all the letters lowercase. So now we have lower being lowercase again, and we change upper, which is lowercase here, to uppercase. So lower, upper, switch them together. We have more of these we can use, like substring. Because these are just a sequence of characters, we can take out any subsequence of it that we want, any chunk of it. So here, we're taking sequence of 4 through our index first character when you start counting at 0, so the second character all the way through the 5th character, which is the 4th one in index order. And so we're basically taking chunky, and we're taking off the first and last letter, which makes it honk. Oh no, I did this wrong. I must have changed this before I was playing with it. There. Honk. All right. There's also commands like trim, which will take the white space off the sides of the character, out of the sides of the string. In this case, we have the string called the size, and it's a big string, right? It goes all the way over here. Bunch of spaces inside the string. We call trim on it, and it takes away all the white spaces on the end. Makes it small again. And you can do trim start and trim end, which will trim either the start of the string or the end of the string. Just trim does both. You can also call repeat. So mushroom emoji, we're going to repeat it 4 times. Mushroom.repeat. And so we get 4 mushrooms. And then another good one to look at in strings is the index of function. So this one's kind of fun. We're going to go inside of our poem fragment here and try to find which index within that string, which character does the word harmony start on. turns out, starts at index 74. Looking at the poem. The word harmony is the end of the second line. And this happens, the H happens to be right at the 47th index character. All right, so this was sort of like an overview on how to use strings. What strings can do, what things you can do with it, what ability to manipulate it we have. And we'll be doing the same thing for numbers soon as well. We'll go over the math operators and things. Oops. All right, do you feel you know strings a little better today? Data structures, variables? All right, any questions about this? Feel like you can reproduce this? I can ask you to do variable things with strings? No? Well, we'll have some labs. We'll get you there. So there's a lot here. I mean, you should know some of the basics of this stuff. But we will, you know, there's just a lot of practice that needs to happen to cement these skills, and that's sort of what the labs and the assignments are for. All right. I'm going to end the recording now.